because it's been nominated for the Best Paper Award, so please attend it carefully. The title is Competitive Prediction Aware Online Algorithm for Energy Generation Scheduling in Microgrids. Ali, go ahead, please.
Thank you for the introduction. So, can you guys see my screen?
Yes, perfect. I can hear you.
Great. Thank you everyone for being here. My name is Ali and I'm currently a PhD student at Texas A&M University. So today I'm going to talk about an important problem in designing prediction-aware online algorithms for energy generation scheduling in microgrids. This is a joint work with Professor Ming-Hua Chen from City University of Hong Kong and Professor Sid Chow from the Australian National University. I hope you enjoy it. So as you may know, microgrid is regarded as a promising paradigm of future power system. While in our current power system is a centralized system, in microgrid, various energy sources such as renewable sources, along with a CHP generator and external grid, natural gas provider contribute to fulfill the time-varying energy demand of a campus-scale community. Microgrid has various benefits, including improving reliability, generation efficiency, and it also helps to integrate more and more renewable into the grid. Because of these various benefits, we've seen the worldwide total installed capacity of microgrid increasing. It was 3.5 gigawatt in 2019, and it's expected to reach more than 22 gigawatt by 2028. At the same time, the market cap for microgrid has also been expanding quickly, as you could see here. Among many problems in microgrid operation, a key problem is how to schedule the output level of local energy sources, as well as the on-demand request from the external grid and natural gas provider to supply the net demand in the microgrid, and at the same time minimize the operational cost, where operational cost basically consists of the cost of the local generation, as well as buying electricity from the external grid and buying gas from the natural gas provider. So as you can see here, the inputs to this problem are the time-varying electricity and heat demand, as well as the market information, such as electricity prices and natural gas tariffs. When the source of the local generation are renewable wind and solar generator, and also local CHP generators. Our goal is to schedule various energy sources while minimizing the operational cost of the microgrid. So in recent years, because of the increasing uncertainty on demand and deploying small-scale renewables, we have seen the uncertainty and intermittency increasing on both the generation side and the load side. As a result of this, it's almost impossible to accurately predict the whole time horizon for the scheduling purposes. That's when online scheduling solutions are needed to help us to overcome these types of challenges. Toward that end, Lu et al. Proposed a deterministic online algorithm called Chase, which I will introduce later in this talk. And the competitive ratio of Chase is basically 3, which means that the cost incurred by Chase is at most 3 times the cost of the minimum offline algorithm. And they've also proposed a prediction-aware online algorithm called Chase with look-ahead, but this algorithm fails to utilize all the predicted information. So in this work, we are designing a competitive prediction-aware online algorithm for energy generation scheduling in microgrid in the presence of the accurate prediction of the future information. We propose an algorithm called Chase PP that improves both the theoretical and empirical performance of the state-of-the-art and achieves the following competitive ratio. As you could see in this competitive ratio, W is the size of the prediction window. And when the size of the prediction window goes to infinity, the competitive ratio approaches to 1, which basically means that our algorithm converges to the optimal offline algorithm. We also introduce a novel design space called cumulative differential cost, and this design space helps us to make more competitive, intelligent online decisions. In this work, we also extended to previous settings and introduced a general setting where we could have heterogeneous local generators, each having a different capacity. In this work, we also characterized a non-trivial lower bound for the competitive ratio for any prediction-aware deterministic online algorithm possible for these types of problems. So in the followings, I will be your guidance and walk you through the journey in this work. I'll be starting with the problem formulation. So the problem we are trying to solve here is called a microgrid cost minimization problem. As you could see, the cost, it has different parts. We have the cost of buying electricity from the grid, also the cost of buying gas from the natural gas provider. We also have the local cost of using the local CHP generator. But the most important part of this cost is this part, which is the startup cost of the generator. As you could see, beta is the startup cost of the generator, and usually the startup cost is a large value, which means that you don't want to turn on and off your local generator too often. A problem that beta creates and this startup cost creates for us here is that this makes the decision and the optimization coupled across different time slots. So this optimization problem has different constraints. The first constraint is the capacity constraints of the local generator. We also have two covering constraints for the electricity demand and the heat demand. And the decision variable, the optimization variable here is YT, which is a binary variable taking values 0 and 1, and that's the generator status. 0 being that the local generator is off, and 1 being the local generator is on. So to better explain what's the real challenge in decision making in this problem, we have actually two sources of supply. We have the external grid as well as the local generator. The external grid is on demand. We could always use it, but it's more expensive. On the other hand, the local CHP generator is cheaper, but we can't use it that often. We can't just turn on and off because of the huge startup costs we have. So basically, when we have a dense demand coming in, for us, it makes sense to use the local CHP generator because we turn on the generator and we use this huge amount of demand that's coming in, and the benefit we get from doing that can compensate the large startup cost. On the other hand, if we have a sparse demand coming in, we don't want to use the CHP generator. We prefer to stick to the external grid and use the expensive cost and avoid spending the large startup cost of the local generator. So let me talk about the existing solutions to solving this problem. To understand the existing solutions and the offline optimal solution, I'll introduce delta T, which is a cumulative cost difference between using or not using the generator. And delta T takes value between minus beta and 0. And based on the values of delta T, we divide the whole time horizon in 4 different segments. These segments are called type start, type 1, type 2, and type end. Type start and type end are self-explanatory, but I'll talk about type 1 and type 2. Basically, type 1 is a special kind of segment when delta T increases from minus beta to 0. And type 2 is a segment where delta T goes from 0 to minus beta. As you could see here, when we have a lot of demand coming in, when we have dense demand, delta T keeps increasing. So that's what delta T is doing. It's capturing the sparseness or denseness of the demand. And when we have a sparse demand, delta T keeps decreasing. So it's been proven that the offline optimal solution, when we have all the future information, is that to turn on the generator when we are in type 1 and turn it off otherwise. So what about the online case when we don't have all the future information? In the online case, we cannot detect the segment type right after entering it. For example, when we are in type 1, we can only detect type 1 when we reach 0. So that's when we turn on the generator. And for type 2, we just turn it off when we reach minus beta. So that's the online solution. And now for the prediction-aware online solution, Chase LK, we can turn on the generator for the online case W time slot sooner than the oblivious online algorithm, because W times last sooner, we know that we're going to be reaching 0, so that's when we can turn on the generator. So in sense of the existing theoretical results, it's been shown that Chase, which is the oblivious online algorithm, achieves the competitive ratio of 3 minus 2 alpha, where alpha captures the maximum price discrepancy between using the local generator or buying electricity from the external grid. For example, if alpha is equal to 1, which means there's no difference between local or external, then the competitive ratio reduces to 1. On the other hand, if we have a prediction window size of W, the competitive ratio becomes 3 minus 2 of f of alpha and W, where f of alpha and W is taking values between alpha and 1, and it captures the benefit of lookup. So now I'm going to explain our novel prediction-aware online algorithm design space. To do that, we have explored this new design space called cumulative differential cost in the prediction window. We define delta from T to T plus W as the cost difference between using and not using the generator in the prediction window. What delta is doing here is that, for example, if we have electricity demand coming in, that is a small value, that's a small demand, then the cost difference between using or not using the generator is actually small in that prediction window. But if we have a large demand, a dense demand coming in, then the cumulative differential cost in the prediction window would be a large value. What this means is that if we have a large cumulative differential cost, we are more encouraged to turn on the generator. But when the cumulative differential cost is small, it's less than a certain threshold, we don't want to do that. We don't want to spend the huge startup cost that we have. So using this new design space and other intuitions, I'm going to give you an idea of how to use this in designing different online algorithms. So consider this example here. When we have type 1 and type 2, and for both of them, actually you could see that the prediction-aware online algorithm turns on the generator W times slot before reaching 0. For both of them, it happens. When it detects type 1, it turns on the generator. But you could see that in this case, the value of the cumulative differential cost is very small. It's near 0. But here we have a large differential cost. So our idea suggests that in this case, you shouldn't turn on the generator. If the cumulative differential cost is less than a certain threshold, you keep the generator off. But if it is larger than a certain threshold, you turn on the generator. There are various intuitions for doing that, but the first intuition is that when you have a small cumulative differential cost, basically there is no gain in turning it on. There is no difference in using on or off generators. So why spend the huge startup cost? But here, when you have a lot of demand in front of you, you want to turn on the generator and use that benefit. The second intuition is that, as you could see, for example, in this picture, when you are in this point, you've already lost all the demand possible in type 1. So it's already too late. You won't gain anything from turning on at this point. But in the second example here, when you turn on at this point, you have most of the demand in front of you. So you could use that incoming demand to your benefit. So this is what we are proposing. We say that when you detect the type, that's not enough. You shouldn't just imitate the oblivious online algorithm. When you detect the type, look into the future and compare the cost in the prediction window to decide. So what we do is that we solve a second optimization problem to obtain the optimal threshold for turning on and off the generator. And by solving that, we get this A star. So with this in mind, let me talk about our theoretical guarantees and numerical results for our algorithm. So we proved that the competitive ratio of our algorithm is 3 minus 2 times G of alpha and W, where G of alpha and W takes value between alpha and 1. And it depends on the value of W and alpha. As you could see here, the competitive ratio is between 3 and 1. And by increasing the window size, the competitive ratio keeps decreasing. The same story here for alpha. And we also develop a lower bound for the competitive ratio of any deterministic online algorithm. We show that the competitive ratio is lower bounded by this value, where delta 2 star is the constant that could be obtained by solving an optimization problem with system parameter as input. So to better understand how our algorithm is compared with the state of the art and with the lower bound, you could see here that the competitive ratio of our algorithm is away from the lower bound. When we have a few hours of prediction, which is a reasonable assumption in practice, we are away from the lower bound by only 9%. And we are always doing much better than the lower bound, the competitive ratio of the previous online algorithm. As you could see here, when we are plotting the competitive ratio improvement as a function of W and alpha, you could see that our algorithm improves the competitive ratio of the state of the art by nearly 25% at some points. So, but theory is never enough. We want to make sure that our algorithm also performs well in practice. So that's why we obtained electricity and heat demand traces from a college in San Francisco. And we also obtained the renewable outputs from a nearby wind station to compare the performance of different algorithms. We consider the optimal offline algorithm, the oblivious algorithm Chase, the state-of-the-art Chase LK, and our algorithm Chase PP. We also look into a popular algorithm called receding horizon control and compare their performance for different window sizes. As you could see, by increasing the window size, all of their performance is getting better. But at the same time, our algorithm is outperforming all possible algorithms out there. And you could see at the beginning, receding horizon control is not performing, like it's performing really poorly, but by increasing the prediction window size, they are getting much better. So, but the natural question rises, and that's you are assuming that you have a accurate prediction of the future information in a certain window size, but that's never true. Always the prediction of the future information comes with some sort of error. So to understand the impact of those errors on the performance of our algorithm, we are adding errors on top of our wind prediction and heat demand predictions. We are increasing the error on the wind prediction by 0 to 100% of the total installed capacity, and for the heat from 0 to 100% of the total peak demand. And we are comparing two prediction window sizes of W equal to 1 hour and prediction window size of 3 hours. In the case of 1 hour, you could see when we are increasing the size of the error, both of the algorithms are relatively robust to the error and they keep their performance. But when the prediction window size increases and we keep increasing the error, the performance of the state of the art keeps deteriorating and it loses its performance. While the performance of our algorithm is relatively robust to this error and it doesn't lose much of the performance. So the reason for that is that our algorithm is focusing on the whole prediction window, not just detecting the type of the type 1 or type 2. It's not just focusing on the segment type, it's focusing on the whole cost in the prediction window, which makes it more robust for in the sense of the prediction errors. So
Ali, could you wrap up in the next 2 minutes, please?
Sure. So with that, I want to conclude the paper. I want to thank Professor Chen and Professor Chow for their contribution and their insightful comments and discussion. And here's a list of our references. And thank you everyone for listening, and I would be happy to answer any question you might have.
Thank you, Ali. Thank you.
Thank you.
And indeed, other questions? I don't see any question on this lecture. I don't see any question in the chat. everybody seems to be extremely happy with your talk.
Thank you, appreciate that. And if you have any question, please feel free to reach out and we'll talk offline.
Okay, thanks a lot. So this concludes this session with the best paper candidate presentation, the last paper. And I think I'm handing over now to Prashant. Sebastian, who's going to take over?